Hey everyone, I'm Victor Muha, a PhD student from TU Wien and R&D engineer at SoftServe. Today, I'm going to talk about our work on egocentric 3D hand pose estimation, specifically how to make it actually work in cross-domain scenarios. So here's the core idea. We improve how well a hand pose model generalizes to new environments, cameras it's never seen before, by training it to regress coordinates in virtual camera space, and then letting it fine-tune itself at test time without any labeled data. Hands are everywhere in egocentric video, whether you're doing AR, recognizing actions, or teaching a robot to manipulate objects. So accurate 3D hand pose estimation is really important. The problem is, most methods are evaluated on the same dataset they were trained on. But in the real world, you're going to deploy your model with a different camera in a different environment. And when that happens, performance drops. Why? First, 3D annotations are really expensive to collect. You need multi-camera rigs or motion capture labs. So models end up trained on limited, lab-only data. And second, models overfit to the specific camera intrinsics, the focal length, the image resolution of their training set. So when those change, the depth estimation falls apart. Our base model is a single-stage architecture, meaning we go directly from a full RGB frame to 21 3D key points per hand. No cropping, no two-step detection. We call our full method VHPOT, Virtual Camera-Based Hand Pose Optimization at Test Time. The first component is about how we represent depth during training. Normally, models predict Z in metric space, actual millimeters, but that representation is tied to the camera's focal length and image size. So if you train on one camera and test on another, your depth predictions are off from the start. We fix this by transforming Z into what we call virtual camera space. The idea is simple. We normalize depth by the focal length and image resolution. So every dataset effectively looks like it came from the same standardized camera. This makes depth predictions more camera agnostic. And as a nice bonus, this normalization also unlocks depth augmentations during training. We can scale images as if the camera moved closer or farther. The second component is a two-part story, training and test time. During training, we add an auxiliary task, pseudo-depth estimation. We use DPT hybrid, a strong monocular depth estimator, to generate depth maps for our training images. These become supervision labels for an extra output head. Why does this help? Because DPT hybrid was trained on massive, diverse data, so its depth maps generalize well. By training our model to also predict these depth maps, it learns richer spatial features that transfer better to new domains. Looking at the depth estimations, we can see that all three datasets look very similar. Here you can see the full training setup, the hand pose head, the depth estimation head. Now here's the really exciting part. What happens at test time? When we arrive at a new domain, we don't just run inference. We first adapt the model using only unlabeled test data. Here's how. The model makes an initial pose prediction. Then we take the same image and simulate it being captured from a slightly different depth. We scale it in virtual camera space. The model predicts a pose for that scaled version too. Since the 3D structure of the hand doesn't change just because the camera moved, these two predictions should be consistent with each other. We enforce that consistency with an L1 loss in 3D space. This updates the backbone weights, not the pose head, for the first 5% of the test data. After that, we freeze everything and run normal inference. And here's the complete pipeline of the test time adaptation. Let's look at the numbers. We train on Hot 3D and test on H2O and assembly hands, which have completely different cameras, environments, and in assembly hands case, even a different image modality. It's monochromatic. This figure shows the loss for each coordinate and how it changes over the test set. The dashed line marks where backbone updates stop. VHPOT improvements are consistent across the entire set. Our ablations show that neither virtual camera alone nor TTO alone is enough. VC fixes the depth representation, but has no mechanism to adapt at test time. TTO without VC still overfits to source intrinsics. Only combining them gives you the full benefit. Looking at the components of our TTO loss function, we observe the best performance when enforcing consistency across all three coordinates, x, y, z, between the original query and two different depth augmentations. We also observe a positive impact of the auxiliary depth prediction task, regardless of whether we use DPT hybrid or a different model, such as depth anything. Finally, we compare VHPOT to Dino V2 with frozen weights, fine-tuned, and as a backbone within VHPOT. The advantage of VHPOT is significant, especially in absolute error metrics. To wrap up, VHPOT is a single-stage egocentric hand pose method that generalizes to unseen domains by combining virtual camera space with self-supervised test time optimization. We reduce MPJPE by 70% on H2O and 41% on assembly hands compared to the base model. We outperform all single-stage competitors and stay competitive with two-stage methods that use up to 14 times more training data. And we do all of this with no extra labels, no pre-training on giant datasets, and no object interaction cues required.